Okay, so this is a super typical optimization problem that involves kind of an area and a constraint equation. So whenever you're dealing with area or something like that, try to draw a picture. So we're talking about rectangular garden, and along one side of the house, um, there's one side of this garden's along the house, but then the other sides have this picket fence. So let's do this rectangular garden. And this part is house. So I don't need fence, or you could label any part you want house, but one side's house. So you only need fencing on three sides. The key is a rectangle. So as soon as I know the shape is a rectangle, I know opposite sides are the same. We have no indication of the length or the width of the rectangle. So I'm just going to assign variables. So again, opposite sides are the same, of course, and then I have this third side, y. I don't need the place along the side along the house. Okay, so, and then a common constraint is like sometimes cost. In this case, it's fencing. So fencing, what does fencing have to do with anything? Well, fencing in this case is the perimeter, right? It's this distance around. And if the fencing, I can only have 40 feet of fencing. Again, recognizing that fencing deals with perimeter. So that's my constraint. So often these problems will have a constraint. So the constraint is the perimeter has to be 40. So I've got 2x plus y equals 40. So that's what I mean, your relationship between the two variables. But then you always, with this problem, go to, okay, what are they asking in the end? They're asking for the largest garden. Largest garden always deals with area. So largest of a space, we're talking about area. So in the end, when I'm talking about largest, it's going to be a maximum problem. So I want to maximize area. And area is just equal to, based on how I labeled my rectangle, x times y. Now, the mistake people make is they want to have like a systems of equations, two equations that are equal to something with numbers, and let's just solve them. But with max and min problems, it's not like that. It's all about working with one equation, getting its derivative, and then setting it equal to 0, seeing if it's a max. So you got to get out of your head that I've got two equations that both equal a number, and then I'm going to solve that system. No. Instead, you're going to be working with an equation and taking a derivative. So I want to maximize area. I cannot take the derivative of this until I have it in terms of one variable. That's where the constraint equation comes in. So I go back to my relationship between the two variables. So I've got y equals 40 minus 2x. And now this is going to allow me to write area in terms of one variable. So area in terms of x is x times, I'm substituting in what y is in terms of x. And now here I have an equation for area in terms of only x. And for max min problems or optimization problems, we know that the first thing we do is take the first derivative. So I'm going to do that. So negative 4x plus 40. Set it equal to 0 to find a critical point. That could potentially be a max or min, depending on what type of problem we have. There's only one case where this is going to equal 0, and that's at 10. And what were my units here? So feet. So let's see if that indeed is a max. He or she, whoever your professor is going to want you to prove that there actually is a max at 10. So that involves taking the second derivative, which is negative 4. And so because the second derivative is always negative, I know the second derivative at 10, of course, is always negative 4. And when a second derivative is less than 0, it means it's concave down there. So yes, there will be a max at x equals 10. So let's go back to what the question was asking. It said, find the dimensions of the largest garden. Okay, I just found the x dimension. The x dimension is 10 feet. And let's go back to the relationship between x and y to find the y dimension. So y then is going to be 40 minus 2 times 10, or 20 feet. So the dimensions are 10 feet by 20 feet. That's the dimension of the rectangle that will give you the largest garden. So again, think to yourself, okay, what's my relationship? First, draw a picture and put some variables to that and paying attention to what the figure is. And then you should have some equation that relates those variables. And then you go to what equation am I actually trying to max or min? In this case, because we're talking about largest, it was going to be of a space. We're talking about area. And then you use that constraint equation to write the area in terms of one variable. And then you go through your derivative stuff. Okay, hopefully that helped.